Just want to remind everyone to please keep your phones on mute so we don't have any extra noise. I'm going to go ahead and introduce Iris, and then we'll let her get started. Dr. Iris Tien joined the faculty in the School of Civil and Environmental Engineering at the Georgia Institute of Technology in 2014. She received her PhD in Civil Systems Engineering in 2014 from the University of California, Berkeley. Dr. Tien's research interests are probabilistic methods for modeling and reliability assessment of civil infrastructure systems. She has a unique interdisciplinary background that encompasses traditional topics of civil engineering, sensing and data analytics, stochastic processes, and decision-making under uncertainty. Previous recipient of the NSF Engineering Innovation Fellowship, Tien was recently selected for the NSF Early Career Investigators Workshop in Smart Cities and the National Academy of Engineering U.S. Frontiers of Engineering Symposium. And her work is highlighted at the National Academy for Engineering, Government, University, Industry Research Roundtable at the Critical Infrastructure Security. Iris, go ahead.
Great, thanks, Andrea. So I'd like to thank everyone for joining this webinar this afternoon. And today I wanted to talk specifically about the work that we're doing as part of our CIRI project on mapping infrastructure interdependencies. And so, overall, the focus is on mapping infrastructure interdependencies, and I'll start with a discussion of why it matters, why it's important. And then I'll talk specifically about the research that we are doing in this area. And I'll focus on three specific advances that we've been making in this area. Related to the first one is in defining comprehensive and generalized infrastructure interdependencies. So there's three specific types that we discussed that we've defined. The second main topic that I'll talk about today is a new framework that we've been developing to model and analyze systems. So I'll go through some of the details of that framework. And then the third main area is this idea of identifying critical components in the network to prioritize investment to increase resilience. So these are the three main research areas within this larger umbrella of mapping infrastructure interdependencies that I'll talk about today. And for all of these areas, I'm going to talk about it also within the framework of ongoing work that I'm doing with the City of Atlanta. So really taking research from academia into the real world to look at real systems. And then I will conclude with a discussion of what these types of techniques and methods can be used for moving forward. So to start off, why does it matter to map these infrastructure interdependencies? So traditionally and historically, infrastructure has been designed and managed in silos. So each department is responsible for their specific resource and their specific type of infrastructure that they're interested in. But we know that there's this increasing connectedness of infrastructure. So as an example, on the right-hand side here, I've shown a figure. This is at a county level in Tennessee of these water system is in blue, the power system is in red, and then the gas system is in black. And so we know that all of these systems are overlaid on each other. So it doesn't really necessarily make sense to think about these systems separately. And so as part of this increasing connectedness of these systems, we have this increasing threat of cascading failures. And we've seen this in several disasters and kind of threat scenarios that we've experienced in the past in terms of a failure in one system cascading not only through that particular system, but cascading to other systems as well. And then in addition to this threat of cascading failures, we also want to be able to take into account geographical hazard. So geographical in the sense of if systems are close together, they might be more likely to fail under the same scenario. And geographical kind of suggests physical proximity, but it could also be kind of functional proximity as well. So if all different types of components are connected to the same control system, that might introduce some additional vulnerabilities as well. And then the third influence of these increasing connectedness between systems is that when we look at resilience and we're thinking more about recovery, there are certain infrastructures that are needed to be able to recover other systems. And so we want to be able to include those dependencies for recovery of infrastructures after any disruptions. And so what we're trying to do here is we want to have an ability to capture in terms of both mapping these infrastructure interdependencies and also quantifying their effects of these relationships between different systems, with the overall objective then to be to change how infrastructure risk assessments are conducted. So instead of just taking into account the performance of a single system, we want to be able to look more holistically across the network to assess the given risk for any system. And then finally, as an overarching goal, we want to be able to analyze these systems in a way that is more rigorous and quantitative and comprehensive than previously possible. So now I'll talk a little bit more about the specific research that we've been doing to address these last 2 points, or these last 3 points on this slide. So the first main area that I'll talk about is defining these infrastructure interdependencies. And so as part of this, we have defined 3 comprehensive and generalized types of interdependencies that we believe fully capture the different relationships between systems. I'll do a summary on this slide and then go into more detail of each of these types on the following slides. So the first type that we defined was what we call the service provision interdependency. So this is when the functioning of one component depends on the service outputs of another to function. So kind of a classic example here is going to be something like a water treatment plant or a water pumping station would depend on power to operate. And so if the power went down, then the water treatment plant might not be able to function as it might have been able to in the past. So that the power is providing that service for that other component in another system. The second main type of interdependency that we defined is this geographic interdependency idea. So this is the idea that 2 or more components in the same geographical area may fail together. And so this is trying to capture these kind of more targeted hazards that might occur that might affect multiple components at once. Then the third interdependency that we defined was really related to this resilience idea, and we called it an access for repair interdependency, with the idea that infrastructure components must be functional for either cyber or physical access to failed components. And so for each of these 3 interdependency types that we've defined, we want to be able to capture those within this quantitative framework, and the approach that we're using is a probabilistic Bayesian network framework to be able to capture some of the uncertainty that's present in some of these systems. And so the material that I'll be talking about in the coming slides is in this journal paper that I've referenced at the bottom of this slide here in the journal called Sustainable and Resilient Infrastructure. All right, so going into a little bit more detail about each of these interdependency types and how we capture them. So for the first one, the service provision interdependency. So again, this is the functioning of one infrastructure depends on the service outputs of another. An example include, so the electricity for water pumps is that second example listed here. But the first example is also fuel supply for power generation. So you might have fuel lines that you need to be functioning into a power generation plant to be able to supply that. And so within so the BN here is the Bayesian network. Within this Bayesian network framework, we can model this direct dependence. So here is an example of what a sample network might look like. So each of these circles are different components in the network. So at this top layer here are the different components, and that yellow arrow in the middle of the graph there is modeling this service provision dependency between the nth power component, denoted C sub NP, providing power to this the first water component here, denoted C sub 1W. And so we can get this direct relation between them. So the state or the functioning of this first water component is going to be dependent on the functioning of that nth power component. And just for clarity for the other layers of this graph, so this second layer here, we're using what's called a minimum link set formulation, which is really modeling resource flows through the network, kind of what are the minimum paths that you need to be operating to be able to take a resource from any source node or supply node to any endpoint distribution node. And so those minimum link sets or MLSs capture that. And then finally on the bottom here we have the overall system functioning. In this case, we just have a water and power network that we're looking at. So that was for the service provision interdependency, and now I will move on to the geographic interdependency. So this is the idea that the functioning of one infrastructure is connected to the functioning of another due to physical similarity or geographic proximity. So examples of this are co-located gas lines and water mains. Maybe in the same trench or in nearby trenches, we have these buried infrastructure that is located close together. So you can imagine they might have some sort of common hazard exposure. So this is, again, the physical proximity here, but you could also have kind of a functional proximity in terms of similar sets of components being controlled by the same system. If that control system goes down, we might have these failures of these close together, perhaps physically similar components downstream. And so within this Bayesian network framework, how we model this dependency relationship is to have what are called parent nodes that capture the hazard. So in this graph here, so the bottom 3 layers are like we saw before previously. Now this is given for the gas and water system, but we can have these common hazard nodes now, which I've denoted hazard 1 and hazard 2, which are capturing the influence of a given hazard or a given threat on multiple components at once. So the idea here is that if a given hazard happens, say hazard 1, we see these 4 dependency relationships coming off of that to the first and second gas nodes, and then the first and n-1 water nodes. And so we see that the hazard effect will propagate through to the component level. And then finally, I want to talk about this access for repair interdependency. So this is the idea that the ability of one infrastructure to be repaired is affected by the access, whether it's physical access or, for example, by a road for a repair crew to go on, or remote or cyber access to kind of ping the asset for a response or to do some sort of remote repair. That ability to access that failed component is provided by another infrastructure that we want to account for. So this really addresses the post-disaster recovery aspect of resilience. And then examples that I've listed here are, for example, communication systems that are required for controls, or transportation systems that might be required to ferry repair crews from their staging site to where the failed component is. So one thing that came up when we were thinking about this access for repair interdependency is this time component. And so within the Bayesian network, we have now a dynamic time component where the idea is that if the infrastructure is functioning as it is, then whether or not the access systems are available doesn't really matter. So if your system is functioning as it normally is, then perhaps the nearby roads that might be required for a repair crew, they're not going to affect the ability for that, say, water system to function. But if we do have a failure, then that's when the importance of those access systems comes in. And so we both have a dynamic time component now, and then we have these access nodes that we add for a level of remoteness of a given component. So here we have our Bayesian network again. The bottom 3 rows are as what we saw previously with the components in the system. And then on the left here, we have now an access node. In this case, it's a road node. And then we also have this previous state node, which captures that time component. So the idea here is to be able to capture kind of this dynamically evolving system over time, tracking how it's doing. And then if something goes down, if something fails, that's when this access for repair becomes important, and to be able to capture the nodes that are required to be able to do any sort of repair. So that is, those are the 3 types of interdependencies that we defined. And now I want to move to talking about, now that we have this idea of what types of interdependencies we want to capture, we built this framework, this new framework to model and analyze systems. So I'm going to show the full framework on the left here, which is a little bit much, but I'll go through each of the steps here to talk in more detail about what we're doing. And then this framework was recently published in a journal paper that is listed at the bottom of the slide here in the American Society of Civil Engineers Journal of Computing and Civil Engineering. So I'm going to go through each of these levels now. So if we look at this first level here, so these are really the inputs to the framework. So we wanted to make it as simple and as kind of low barrier to be able to start building these models as possible. And so we really want to just take basic component information that any utility or any municipality should be able to have. I will say, kind of in working with utilities and municipalities, that might not be the case, but this is really what we think is the bare minimum of what should be required. And so this is basic individual component characteristics. So the first element is location coordinates and connectivity pairs. So this is where each of your components are and how they're connected. And so that will tell us where everything is located and how the system is connected. The second is the type of component is important. So this is whether it's a supply component, a distribution component, or a transshipment component. And so that'll affect the functionality of that particular component within the network. And then the last input is going to be an input failure probability. So what is the likelihood of that particular component functioning or not functioning under different scenarios? So this is probably, I would say, the trickiest part of this framework in terms of these inputs. So these failure probabilities can be empirical if you kind of measure certain failure rates over time. And talking with different utilities, several of them have types asset health scores for different elements of their system, and so those health scores could be translated into a corresponding probability of failure for any individual component. And then, of course, you could also, with owners or operators or other experts with the system, they could estimate these failure probabilities. The last thing I would say about that is that if you don't have exact numbers, you could still do kind of relative analyses to see relative rankings of the importance of different components, even if you don't have the exact precise number in terms of the probability of failure. So once we have these individual component inputs to the framework, then the next level here is what I've listed here as minimum link set identification and supercomponent identification. So these are really to reduce the dimensionality of the network that we're interested in. I won't go into too much detail here, but the overall idea is to make the analysis computationally tractable and scalable. So as we know, these infrastructure systems are really large and complex, and so a lot of previous methods haven't been able to directly assess or model some of these larger systems. And so this step here helps us be able to apply this methodology and this framework to larger systems than in the past. And so for this particular approach, in the past, you could only look at maybe 10 to 20 type nodes, and now we're applying it to systems with on the order of hundreds of nodes. And so we could look at much larger systems than before. And so the minimum link set identification part of this algorithm is to identify those flows through the network. So the minimum link sets, as I discussed earlier, was to map what is the minimum path through the network to convey a resource from any source node to any other node. And so we want to be able to identify all of those minimum link sets in the network to be able to track flows through the network. So one of the outcomes is we want to say, what is the probability that we'll be able to provide that service or that resource at a specific endpoint distribution node? And to do that, we have to say, where is that endpoint getting its resource from, and mapping out those paths. So this is the algorithm that does that. And then the second algorithm here is the supercomponent identification algorithm. And so this is an algorithm to identify clusters of components. And so this helps us kind of reduce the size of the network without losing information. And so that is what that algorithm accomplishes. So once we've reduced the dimensionality of the network, then we can move to this next step here. So here you can see the definition of these three types of interdependencies. So these are exactly the three types that I previously discussed. So these are the three specific interdependency types that we think comprehensively capture the functionality of the network. And so after that, then the next two layers here, I'm not going to go into details here, but these are the steps that are required to build the probabilistic network model. For the person who just joined, would you help to mute your mic? So let's move forward. So these steps here are to build the probabilistic network model. So these are the steps that give us this comprehensive network model. But what I really want to focus on today is kind of once you've built this, what can it be used for? So I'm going to focus now on these last three boxes here, which are the types of analyses that we can do once we have this full model built. So the first, so these are the different types of inference scenarios and the different types of analyses that are enabled from building this full model. So the first box here I've shown as outage simulations. So this is really the ability to look across a range of different threat and outage scenarios and to look at the impacts from a single system. So again, moving beyond a single infrastructure system to look at the interconnected, interdependent network of systems. And so looking at those impacts across a range of different scenarios. The second outcome or analysis that we can do is listed here as vulnerability assessments. And so these are the ability to more comprehensively look at infrastructure vulnerabilities. So one of the things that we were really interested in doing when we started this project is this hypothesis that maybe we don't understand our vulnerabilities as well as we should because we haven't taken into account all of these connections and interdependencies with other systems. And so with this whole framework, we're able to get a more comprehensive view of the vulnerabilities of any given system. And then the last inference or analysis that we do is this critical node identification. So this is the idea of identifying critical components in our network. So really seeing what are the most important components in our network. If we have limited resources, how should we prioritize those resources? With the idea of facilitating more effective investment decisions to increase resilience. So this is the idea that if we can identify the most critical nodes in our network, maybe we should put our resources there, and criticality might be defined as the nodes that contribute most to ensuring resilience of a system. And I'll talk more specifically about the methods that we've done to do this particular step here. But if we have identified those critical components, that is where we want to funnel and target our resources for the most effective investments. All right, so so this is the overall framework that we've used to model and analyze systems, and now I want to talk more specifically about the specific systems that we've been looking at. And I want to talk about this in the context of ongoing work that I'm doing with the city of Atlanta. So I'm at Georgia Tech. We're located right in Midtown in Atlanta. And so it really made sense to do a partnership with the city. It's a very large metropolitan area, a lot of people, a lot of businesses, a lot of important functionality that has to be maintained. And so as part of the CIRI project, what was really exciting is to support this collaboration between these different entities here. So I have Georgia Tech on the left, and then I've been working across these city departments. So first the Office of Emergency Preparedness, and then AIM is Atlanta Information Management, and then the Department of Watershed Management. And so this was kind of a great opportunity to really work across what has traditionally been pretty siloed operations. And by working across these silos, we wanted to be able to identify and map the points of contact between these different infrastructures. The overall goal with the city is to really see it as a municipality that is quantitatively including the impacts of interdependencies on their system risk assessments. And so taking this city almost as the test case for what these types of analyses can be used for. And the scenario that we focused on is this application of water services and power, where we want to conduct risk analyses for the water system, look at their impacts on emergency services, and including the dependencies on power and also cyber to look at what the impacts of those systems are on the water service system. So looking more specifically at the water services and power system that we looked at for our application. So this is kind of a skeletonized version of the system that we looked at. So here, the blue dots here are the distribution nodes. The white circles are the supply nodes. So I will say that it was great to be able to kind of work with a real system and work with the actual end users of the system to get this data and to run these analyses. So this is the a skeletonized version of the overall system that we're looking at. And then we wanted to apply this framework that I described earlier to this particular system. So if we look at this overall framework, I'm going to just focus on those bottom three inference and analysis opportunities at the bottom there. And so I'm going to look through each of those individually now. So for these bottom three outcome analyses that we can do, looking first at the outage simulations. So an example of an outage simulation that we can run is we could say, as shown in the middle graph here, if we have certain failed supply nodes, what are the impacts across the network? And so the right color bar is showing the probability of failure for a given component. So we've mapped all of the components, and then their probabilities of failure are going from 0 to 1. So 1 is that it fails. The blue at 0 is that it survives. And so we see if we have a failed supply node at one part of the network, how it propagates through the network to some degree, but not to the whole rest of the network because we have these redundant supply nodes. I will say that we've also modeled the power supplies at each of the water supplies nodes. And so to capture those dependency relationships there. And then now looking at vulnerability assessments. So here's an example of an inference scenario that we can run with vulnerability assessments. So here in the upper right-hand zone of the system, we simulated a hazard occurring, and we can see these updated assessments of how likely components are to fail in that area. And so these are just two examples of the different types of inference scenarios that we can run. It's really kind of limitless in terms of what types of scenarios you could use to assess your system. One other thing I wanted to highlight before we move on to the critical node identification is the performance of this framework with its algorithms. And so here I showed a table where the proposed method, which is this proposed framework that we've developed, I'm showing the time to do a calculation and then the average error in terms of percent. So I have a 0% error for the proposed method because we're getting exact values in terms of the inputs and the probability values that we get as outputs. And so there's actually no error in that calculation. And one of the kind of main alternatives to this type of approach is to run a bunch of simulations and see what happens, count how many scenarios, run a bunch of simulations, and for each of those simulations count how many components fail or not fail, or in how many instances a particular component fails or doesn't fail. And so for the rest of these columns here, I showed a varying number of simulations. And if we look at this last column here for 10 to the 7 simulations, we see that the calculation time increases exponentially as we increase the number of simulations. So we went from 55 seconds for 10 to the 6 simulations up to 3,600 for 10 to the 7. And as we expect, the average error decreases as we run more and more of these simulations, but the average error isn't really decreasing that quickly. And so this framework is really a way to more quantitatively and rigorously assess these system outcomes without having to run a ton of simulations and without being, and also with the simulations, you're not totally sure of how well you think the system is done. And so without any sort of guarantees on the performance, whereas with this proposed framework, we can be confident in terms of the inferences that we make from our model. And so now I want to focus on this last element here, the critical node identification. And so this will be this third main area of research that I'll talk about today. And so this is the idea that we want to identify the most critical components of the network to be able to prioritize our investment and inform effective decisions to increase overall system resilience. And to do that, then we need to have some sort of measure of importance of a particular component. And then the other thing that we wanted to do as part of this project was to assess the impacts of interdependencies on how we assess component importance. And so we started with centrality-based metrics. So from the graph that we had, or the graph of the infrastructure network, you can see that as a network graph, and there's a lot of different metrics that are available to assess the importance of different nodes in a graph or in a network. And so these are, I refer to these as centrality-based metrics, and they really account for network topology or how different components are connected. So if you think about an infrastructure system, the importance of any given component is probably going to be related to how it's connected in the network, where it is in the network, what its function is in the network. And so these are metrics that are trying to capture that. I'll talk about two specific centrality-based metrics today. So the first is degree centrality, which is just the number of nodes that any given node is connected to. And so this has been used in the past for in social networks to see how much influence a given node has on its surrounding nodes. It's been used in kind of disease spread and looking at the immediate risk of a node being influenced by surrounding nodes. So that's degree centrality. And then minimum link set appearances was the second centrality-based metrics that we wanted to look at. So this is the idea that importance might be a function of how many minimum link sets a node appears in. And so intuitively, this is the idea that if a node is on a lot of paths that are going through the network, going from a source node to a distribution node, then it's probably more important. And so minimum link set appearances was a second centrality-based metric that I'll talk about today. And then in comparison to these network topology based measures of importance, we also have reliability-based metrics of importance. So this is, instead of looking at how the node is connected in the network, this is looking, including information about the reliability of individual components. And so two of the kind of most popular reliability-based measures that are out there are what's called risk achievement worth, or RAW, and risk reduction worth. So risk achievement worth is the idea, we're trying to measure what is the maximum increase in risk if a given node fails. So you can think about, if we have an overall system, it has a lot of different components in it. If one of the nodes fails, it'll affect the overall failure of the system. And so how much it affects the overall system performance will be some sort of measure of importance. And then the risk reduction worth is just the complement of that, where we want to, that's giving us the maximum decrease in system risk with an improvement in node I. So this is saying if we retrofit this particular node to be really strong, really hardened, and to really almost guarantee performance under any scenario, how much does that increase our overall system performance or decrease our overall system risk? So today I'm going to focus on, for the centrality-based matrix, I'll present results for the degree centrality and minimum link set appearances. And then for the reliability-based metrics, I'll focus just on the risk achievement worth. Risk reduction worth is really just the complement of that, so it's not really capturing any new information. So these are the three measures that I'm going to focus on. So in the next slides, I'll present the results ranking these different components based off of these different measures. There's a lot of plots, and I'll try to go through and explain those as clearly as possible. So looking first at degree centrality, this shows here a plot of the rankings of the different components. So before I start, I'll say that this is a material that we've submitted for a journal paper that's currently in review for the journal Reliability, Engineering, and System Safety. So it hasn't been published yet, but hopefully in the coming months it will be. So here on the y-axis here, we're showing the ranking of the particular component. So lower ranking is more critical, so towards the left we have our more critical components. The different gray bands are for different types of components. So on the bottom of the plot you see water distribution, water transshipment, water supply, or power supply components. And so the different bands show what type of component it is. And then the yellow squares here are the rankings including the interdependencies. And then the blue circle there is the ranking without interdependencies. And so if we look at this plot here, so going across the x-axis is all of the individual components, and the y-axis is their ranking. So one of the issues with degree centrality that we see is that there are very few ranking levels. So all the lines go almost straight across, and that's because most of these components have very similar numbers of degrees. So degree, again, is how many connections it has. And so most components either have one connection or maybe 3 connections. And so this is going to be typical for many infrastructure networks. They're built in some sort of branching topological structure, or maybe they're endpoint distribution nodes. In those cases, they'll have these very few differences in the number of degrees that they have. And so here I'm showing a plot of the system with the different nodes colored in terms of criticality. And so although we see kind of some difference between the consideration with power and without power, because we really don't have very much differentiation between these components, we don't think that it should be used on its own to rank components. So even though degree centrality is a metric that is used often in network analysis, we really don't think that it's a good method on its own to rank the importance of components in critical infrastructure systems. So now let me move on to the minimum link set appearances metric. And so here is the same type of plot as the previous slide. On the x-axis we have the different components, y-axis we have the different ranking numbers. And so now we see that there's a larger variation in component importance ranking. So we don't have those straight lines across now, we have some more gradation and more variation in these component importance rankings. But if we look at the plot of the system with the criticality indicated for each node, with and without the power dependencies included. So there actually is not any change with the dependencies on power, because our minimum link sets are going through the water system right now, and so we're not actually capturing, so whether or not a power supply is considered or not, we still have that same minimum link set through the water system, and so that's really not what we want to do. So part of this is we want to see what is the impact of including interdependencies on component criticality ranking, with the idea that maybe if we don't include if we haven't traditionally included interdependencies, maybe we're kind of missing out on what the actual component criticality is. So minimum link set appearances doesn't look like to be a very good metric to use on its own either. And then finally, it also doesn't consider the reliability of individual components. So this is purely based off of connectivity in the network, but we're not looking at individual component reliabilities at all. And so then that brings me to the third metric, which is a risk achievement worth, RAW. And so here I'm showing on the left-hand side here is the map again with the components criticality with power and without power considered. And then on the right-hand side here, I have the component rankings by component type. And then the yellow again is with interdependencies and the blue is without. So one thing to notice here, so first we have a lot more variation now. So we've ordered the components here in terms of ranking by with the interdependency case. And then we see that when we include these dependencies, if we look at the very left side of the right-hand graph, so the gray bars, the water supply and the power supply components are more towards the left. So if we look at the lower ranking numbers, which are more important, we see the water supplies and their corresponding supplies being ranked more importantly. And that kind of intuitively makes sense. So if we're looking at our system, we want supplies are kind of critical for providing that resource. And so the water supplies and the power supplies that provide power to those specific water supplies are going to be ranked more importantly. And one other thing that we wanted to look at to kind of more quantitatively assess the effect of including dependencies or not on the rankings is this plot that I've shown here on the right-hand side here. So what we plotted here was the change in this metric with considering power and without considering power. And so on above that black line there, so essentially above 0, we have components that are more critical with the power considered, and then on the bottom we have the components that are more critical without the power. And so you see from the darker gray band there, the components, the water supply components become more critical once you include the power dependencies in our network assessment. And then one other note is that without considering the dependencies, these transshipment nodes become more important. So these are nodes that go between distribution and supply nodes. But when we looked a little bit more closely at the results, we found that these transshipment components were actually very close to supply components. And so we really thought that that was actually a bit redundant information from our supply component rankings. So that wasn't really what we wanted to capture. And then again, this is including only the individual component reliabilities, but we want to account for both individual component reliabilities and network topology. And so that led us to think, well, maybe we should combine the centrality and the reliability-based metrics. So that's exactly what we did. And so we proposed a metric that is combining this degree centrality idea with risk achievement worth. And so what we did was we weighted our risk achievement worth value by a component based on its degree. And so here, the weighted value, the superscript of A and D, are the risk achievement worth plus degree considered together, which is the risk achievement worth, which is the superscript A, weighted by this lowercase w with the superscript D, which indicates the weight by degree centrality. And so how we calculate this particular weight is that we weight it as the normalized degree value plus 1. And so the right-hand side of the equation here, we have a 1 plus that term there. That term is going to normalize our degree centrality value. And then we add that 1 there because we want components with a single connection to have a weight of 1 instead of a weight of 0. So we don't want the value to be 0 when we're trying to calculate criticality. So we added that 1 there to make sure that the components with a single connection have a weight of 1. And so with this new proposed metric, we ran the same analyses on the network, and these were the results that we got. So on the left-hand side here, we have the results showing the criticality by component with power and without power. And then on the right-hand side here, we look at what the differences are in considering power or not. And so one of the things to notice is that so all of the water supply components are more critical when the dependencies on power are considered. And we know that the supplies are critical to provide a resource, and so it really shows the need to include interdependencies in our system risk assessments. If we didn't include power in our system risk assessment, then the water supply components didn't come out as more critical, or they didn't come out as critical as when we included the power dependencies. But one other thing that we found, so here on the left-hand side now I'm showing the plots by individual component now and by ranking. One thing that happened was that the corresponding power supplies now aren't ranked as highly as they were in the past. And so when we were thinking more closely about kind of what did these results mean, we found that the decreased importance of the corresponding water supplies decreases that redundancy in terms of accounting for the criticality of an individual water supply. So this is the idea that a power supply is really only important insofar as it provides power to the water supply component. So having both components up there is maybe missing out on some other measures of importance. And so by decreasing the importance of the corresponding water supply, we decrease that redundancy, and then we're able to account now for additional centrality attributes of a component importance. And so the last thing that I wanted to talk about with regards to these component importance results was we wanted to do an even more systematic comparison of the metrics. And so what we did was we plotted here, as shown on the right. On the x-axis here, we have the difference between that proposed degree plus raw metric and the criticality with just using the risk achievement worth. And then on the y-axis here, we have the number of connections. So we know that the number of connections a component has should affect how important it is. And so we want to see here we're plotting now the relationship between individual component characteristics and their criticality. And so here we can see this pretty clear linear relationship between the number of connections and the change in their ranking with the proposed combination metric compared to the single metric. And so on the left-hand side here, the components are more critical with the proposed combined degree centrality plus risk achievement worth metric. And so that makes sense because we want to include both their importance from looking at their reliabilities, and then also their components with degree centrality. And so we really think that this combination metric accounts for both centrality-based attributes and individual component reliabilities. There are two outliers that I've highlighted on the plot here. So S6 and S2 are two supply components. So both of these have a lot of connections, but little change in ranking. But they're both critical in both of the measures. And so those are, we really consider those to be outliers within the overall trend. And so from these analyses, we recommend use of this degree centrality and risk achievement worth as a criticality measure for these interdependent systems. And from these studies, we really highlighted and found that it's really important to include these infrastructure interdependencies in our system assessments. If you don't account for these dependencies, you might miss out on some of these critical components that you might not have seen otherwise. And so when we're doing any sort of prioritization or identification of criticality of different components in the system, we found that it really is it is vital to include these dependency relationships in our system assessments. And so the last thing that I wanted to end with today was to talk a little bit about some work that we have been doing in the past year and a half with 100 Resilient Cities. So about 2 years ago now, Atlanta was selected as one of the Rockefeller Foundation's 100 Resilient Cities. So this is a program, I'm sure many of you are aware, that many cities apply to be one of these 100 Resilient Cities. And then as part of this work, so Rockefeller Foundation is supporting this 100 Resilient Cities initiative. And so Atlanta then now has a new Office of Resilience that I've also been working with. And so as part of this initiative, this overall initiative, the idea is to define, support, and implement new initiatives to increase city resilience. And so there's some support from the Office of Resilience. The Rockefeller Foundation supports a Chief Resilience Officer for the city. And as part of this effort, partly due to the work that I had been doing with the city as part of the CIRI project, they asked me to co-lead one of their working groups. And so it's called Discovery. They call them Discovery Areas. And the working group that they asked me to co-lead was the infrastructure-focused one. And so our charge was to strengthen and maintain infrastructure and promote community preparedness. So I agreed to do that. And so over the year, we had many meetings with different stakeholders across the city. So this was both on the public side, so city departments, on with individual utilities and then also with community members. So we had a lot of meetings and kind of focused discussions about how to strengthen and maintain infrastructure for the city of Atlanta to increase its resilience in the years moving forward. And so what I wanted to highlight was from these efforts here, and as part of the 100 Resilient Cities program, the city has to put out a final resilience strategy. And so this is the cover of our final resilience strategy that we did for, that the city of Atlanta now has put out as part of this program. And what I wanted to do today was to highlight one of these action items in this final resilience strategy. And so this is available online and you can look at it, but one of these actions in section 4, which is focused on infrastructure, is action 4.1.2, which is to establish a system and evaluation process for joint infrastructure investments by 2020. And so this was something that really grew out of the interdependency work that we've been conducting as part of the CIRI project. And really in talking with the city and working with them, discussing the importance of including interdependencies in any system assessments and analyses. And so from this work, this action item is to establish this system and evaluation process for joint infrastructure investments. And as part of that, what's happening now is development of what's called a cross-functional infrastructure evaluation board, with the idea that any given infrastructure project shouldn't just be evaluated by the specific system or resources that it pertains to. So, for example, a water investment in the water system perhaps doesn't only need to be or shouldn't only be evaluated by the water department. If it affects emergency services, it's probably important for emergency services to be part of that discussion as well. And this applies for all different types of infrastructure assessments that you can imagine across the city. And so really working cross-functionally across traditional silos within the city to evaluate infrastructure. And so the goal here that we wanted to do behind this action item was to create a more comprehensive and holistic evaluation and to support implementation of these infrastructure projects that are that we consider these effects and benefits across multiple types of systems. And so for the city, of course, there's limited resources, and so part of the impetus for this was also that we could maybe then leverage one system for benefits and efficiencies across different types of city departments. So maybe if we're a little bit more coordinated in our investments and we evaluate these investments with a thought of how they connect across these different sectors, we can have infrastructure investments that are more beneficial and more efficient across the city and increase overall city resilience in a more kind of comprehensive manner. And so with that, I'm going to conclude with a summary of what we've talked about today in terms of mapping infrastructure interdependencies with a focus on what it can be used for. And so I talked about mapping infrastructure interdependencies specifically to account for system dependencies and with the idea of trying to be able to predict or minimize cascading failures through the networks. We want to be able to account for any sort of geographical or physically or close, similar with proximity or similarity in terms of geographical hazards. And then we also want to include dependencies for recovery. So I wasn't able to show some of the work that we're doing now, but in terms of integrating, for example, transportation networks into recovery for these systems. And then I just talked about and kind of described ways that we can address this need for more rigorous and quantitative analysis capabilities, accounting for these system interdependencies. And so really this framework that I presented and the interdependency types that we've defined, we think that they can really be useful for as a framework or as a foundation for conducting these more rigorous and quantitative analyses of interdependent systems. And then finally, once we've built these models, run these analyses, and we get a better sense and a more comprehensive view of the different threats and vulnerabilities of critical infrastructure in a way that is more detailed and kind of more quantitative than previously possible. And so with that, I want to acknowledge current funding support from these projects, and obviously specifically from the Department of Homeland Security through CIRI for this particular work that I talked about today. And I have my contact information here, and I would be happy to take any questions that people on the webinar might have right now. Thank you very much.
I'm going to go ahead and unmute everyone to see if there are any questions.
Any questions from any listeners?
Someone typed in a question and asked if the slides will be available, and yes, they will be uploaded to the CIRI website in a couple of days, and I will send out an email when that happens.
Great, thanks, Andrea.
Oh, wait, that's a question by chat too. Someone asked, how are you collecting data to run the models?
Yeah, so that was, well, as CIRI knows, and kind of over the last couple of years in working with this project, that was definitely actually one of the big efforts in the first year of this project, was getting the data and working closely with the city to get the proper data to run the models. And so that was, so now the data that we're using is really from a pretty close collaboration between us as a research team and the Department of Watershed Management and Office of Emergency Preparedness in terms of getting the right input data for the models. So it's definitely an ongoing process in terms of getting data at the resolution and granularity that we want. But I think, as we've shown in this project, and I think in general, it is important to work with the end user stakeholders as closely as possible to get as accurate and as up-to-date information as we can to run any of these models or analyses.
Okay, and then there's another question. Hold on just a sec.
Okay.
Oh, one question that asked about, oh, here we go. It says, do you have any private sector input from this process? Specifically private utilities?
So we have not worked too closely with any private utilities yet. So I've talked to a few private utilities, just how it's set up at City of Atlanta. It has a different kind of organizational structure there. So we haven't. I can imagine that. So I know, so like kind of like those asset health scores that I had mentioned for some utilities, that they have those to assess. They're based off of age or material or where they're located, and that's typically what, if they do have that, that's what they use to do some of this component prioritization. So I think that this methodology would complement that type of approach pretty well in terms of using that as input data, but being able to see kind of more system level effects of an individual component on your overall network instead of just looking at individual elements of your network. And so I think it would complement pretty well with what I know of what some private utilities are doing right now in the risk assessment and vulnerability assessment space.
Okay, and then another question, how long is the city typically funded through the 100 Resilient Cities program?
So that I am not sure, actually. Yeah, I'm not totally sure. I think and the Rockefeller Foundation funds the Chief Resilience Officer position, and there's kind of opportunities to apply for projects for support through some of their partners. And so the support is really like an in-kind support, less so than specific financial support for specific projects. But I'm not totally sure in terms of how many years forward we're moving. I mean, for the state of Atlanta, so we just went through a mayoral change as well, and so that kind of led to some changes as well. But I know that it was a big priority of the outgoing mayor, and he kind of saw this project in the final resilience strategy as one of his kind of hallmark achievements while in office. And I know that the new mayor is very supportive. And I've met with some members of the new administration as well, and they are also kind of excited about these opportunities moving forward. And I think being one of the 100 resilient cities offers a lot of exposure and kind of a platform with which we can maybe do new things that either are related to Rockefeller Foundation or even not, but kind of leveraging that support in terms of in-kind support and that network between the different cities to pursue other opportunities, whether it's within Rockefeller Foundation or outside.
Great, thank you very much. Are there any other questions? Well, it looks like we're almost at the end of the time period. And I just want to thank you, Iris, very much for giving the talk. Also, we have another talk coming up in December 13th at 1 p.m. Central Time. It'll be Sachin Shetty from Old Dominion University, who's also a CIRI researcher. Thank you all for being on the call.
Thanks.